Hi there, I'm Miquel Massot. I'm a senior research fellow at the University of Southampton, and I'm going to present a paper titled Development of a Passive Drifting Seafloor Imaging Float with Hybrid Altitude and Illumination Control for Increased Survey Endurance. The authors are Andrew Borg, Jonathan Boschen-Rose, Blair Thornton, and me.
There is a persistent need for seafloor exploration, especially with underwater imaging. If we compare the ocean to Mars, the planet next to us is 55 million kilometers away. More than 99% of its surface has already been mapped at a resolution of 20 meters. However, the ocean, which is right here, we have only explored a fifth of it acoustically, 200-meter resolution. If we look at the image in the center, that's the city I live currently, Southampton. From the picture, you can tell roads, buildings, parks. But if you look at the image on the right, where I have downscaled it to pixels of 100 by 100 meters, we can hardly tell that there is a city there at all. But as I said, this 100-bit resolution exploration is based on acoustics. If we look into how much of the ocean has been seen through the eyes of a camera, that's less than 0.1%. So how do we deal with this massive task sustainably? Okay, let's look at the reasons why we would use imaging in the first case. There are four major use cases: routinary inspections and interventions of underwater infrastructure, monitoring of marine protected areas, or MPAs, baseline surveys to compare to other campaigns to other deployments, and also pure exploration. These are normally carried out by either ROVs or AUVs. These are remotely operated vehicles or autonomous underwater vehicles, during a cruise that can last anything between a week and a month, with repeated surveys on the same area, with high logistic costs and expensive platforms. However, if we look at the targeting and knowledge requirements of the work area, we can differentiate four quadrants: highly targeted regions with lots of knowledge about, or low targeted regions with no knowledge at all. Currently, all these different scenarios are covered by the same platforms, AUVs and ROVs, with the same expensive costs and complex logistics. To cover more ground, increasing the number of AUVs and ROVs with the same number of people and research vessels is not going to work. We believe that there is room for improvement. Loosely targeted platforms, such as Lagrangian floats, can be used instead to lower costs and achieve a massive scalability. These drifters do not have means of self-propulsion. They drift with sea currents instead, just controlling their altitude with respect to the seafloor. They can be left unattended by humans for several days or weeks while they collect data. They can be loosely targeted to pass over regions of interest using seafloor current predictions. Floats are more affordable because they don't rely on expensive self-localization sensors. This enables their endurance to last for longer periods compared to UVs. However, if we look at their energy expenditure, the major part of the energy is used to fight against non-neutral buoyancy. If we can find solutions to decrease their power consumption, we will be improving their mission lifetime and overall performance. In this work, we will be looking at how we can improve their image quality and improve battery life. Current underwater platforms, such as AUVs or ROVs, keep constant altitudes to the seafloor whilst imaging, with fixed frame rates, illumination, and camera exposure to ensure good image quality. But what if image quality can be optimized for better energy efficiency? We propose an adaptive illumination control, where light intensity is modified based on altitude to achieve higher dynamic ranges, and the frame rate is controlled to ensure image overlap based on visual odometry. This can be seen in the diagram below, where the drifter loosely keeps its altitude with the seafloor to save energy and modifies the camera frame rate and exposure to ensure good image quality and overlap. To do this, we need to understand underwater image formation. Let's follow the course of light. At first, the light source, in green, casts light in the environment with a particular power distribution. This light is transmitted and absorbed by seawater until it reaches the seafloor. We will assume that the seafloor has a perfect specular reflection for simplicity. Then this light travels to the camera. Its sensor receives a different power distribution, and its Bayer lenses turns into RGB, that's red, green, and blue signals, which are finally translated to pixel values. We can see how the light source power distribution is affected by absorption after traveling 8 meters, the equivalent to 4 meters altitude. The red part of the spectrum is mostly affected, almost decaying to zero, whilst the blue part of the spectrum is almost the same. This light reaches the camera sensor and gets converted to RGB values. As we see, the amount of red lost is more significant than green or blue, and therefore underwater images suffer from a lack of red color in their images. A common issue on this is to find the correct exposure to sense enough red without saturating green or blue channels. Having said this, we have to answer the question of what makes an image good. We believe that the good image is not blurred, not saturated, and has enough signal-to-noise ratio. We therefore develop a reward function based on this. It's got 3 major scores: blurring, dynamic range, and signal-to-noise ratio, or SNR. To check that an image is not blurred, we have to compute the maximum exposure time, Tmax here, as the quotient between the blurring distance and the speed. Assuming 1 pixel of blur, the maximum time is defined as the pixel resolution R divided by the speed and the focal length in pixels. For this formula, we need velocity measurements that have to come either from a DVL or visual odometry. The score for this is binary, and an image will not be considered blurred if the exposure time is less or equal to this. The second score is the dynamic range. With it, we check that we are not saturating any channel and that red is detectable. Dynamic range is usually defined as the relationship between the full well capacity and the readout noise. The value of KDR is 1 if the number of electrons in the red channel is larger than the bit depth times the readout noise for the camera, whilst the other channels are not saturated. And finally, the score for signal-to-noise ratio. With this, we verify that the noise in all channels is below a threshold parameter. The SNR is defined as the relationship between the number of electrons in a channel versus gamma times the readout noise. These 3 scores are averaged to obtain an image quality metric. This value is computed recursively for different values of exposure to get good quality images. This method has been tested under simulation, where the drifter has been modeled using the following net force equation. Mass times acceleration equals to gravity force minus drag force minus buoyancy force plus thruster force and plus variable buoyancy engine force. We assume that neutral buoyancy of the float can be achieved at depth using a VBE. The thrusters are controlled using a proportional integral derivative, a PID controller, and an altitude set point of 3 meters. 2 different controllers, one fast responding with a high power demand and one slow with a low power demand, are compared over a square wave-like terrain with 10-meter long steps changing 1 meter of depth. In blue, you can see the platform response to the terrain following. The simulation follows 3 steps: a constant descent using a VBE, an altitude keeping step using only thrusters, and a constant ascent using the VBE. Different seafloor currents varying from 1 centimeter per second to 50 centimeters per second have been considered. In each scenario, we evaluate IQM, that's the image quality metric, and check how many valid images are gathered, taking into account that the valid image has a score of 1. Likewise, the strobe duration, or conversely, the exposure, is also changing throughout the dive. The results show that adaptive illumination control is able to record valid images for all different current speeds, whereas fixed illumination decays with increasing speeds due not only to blur but also to poor exposure times. In terms of power consumption, we can see that adaptive illumination is able to save power on low currents. In the last scenario of currents of 50 centimeters per second, We see that the trend has inverted, but this is due to guarantee image overlap. In this scenario, a fixed frame rate would not have overlapping images needed for visual odometry. We've proceeded to design, build and test the Lagrangian float described before. Our platform, named Floaty Float Face, or Floaty for shorten, is a 60 kilogram drifter with a depth rating of 200 meters and an endurance of 9 days. It houses a stereo camera rig, seen on the right hand side, a pressure sensor, an IMU, GPS, altimeter, and a LED strobe. It uses Wi-Fi and an acoustic modem for communications, and we included Iridium for a safe latent recovery. The platform has been tested in a cruise in Norway, and it's now being shipped to Spain for another cruise. In conclusion, we've presented an image quality metric to find and evaluate the best imaging parameters and used it for adaptive illumination control. With this adaptive control, we've demonstrated that platform endurance can be increased by saving power. However, this solution requires achieving neutral buoyancy and be able to measure its velocity. Our future work includes an experimental demonstration of this adaptive illumination control and the integration of a newly designed VBE in the drifter. We will be joining a cruise from the 14th to the 20th of September with Floaty to gather underwater images of the Mediterranean Sea.
Thank you very much for listening, and I hope to meet you at another conference. Goodbye.